Good afternoon, everyone. Thank you for joining my presentation. My name is Zhensong. The topic of my presentation is Design Connected Eco Approach and Departure System for Electric Trucks in PTV Vissim. Trucks play an important role in the US economy by transporting large quantities of raw materials or finished goods over land among seaports, manufacturing factories, and distribution centers. In 2019, the trucking industry has hauled 12 billion tons of goods. That's over 70% of all freight transported in the United States. The transportation sector has become the largest contributor to the US greenhouse gas emissions. Among the 5 main transportation sectors, medium and heavy-duty trucks, which make up only 4% of vehicles in the US, produce over 20% of all the transportation greenhouse gas emissions. To save energy and reduce emissions, more energy efficient and environmental friendly fuel sources, such as electricity and hydrogen, have been applied to zero emission vehicles, including pure battery plug-in electric vehicles, plug-in hybrid electric vehicles, and hydrogen fuel cell electric vehicles. Electric trucks have been widely studied due to the high efficiency of the electric powertrain and low running costs, and are becoming a promising alternative to traditional diesel trucks. In California, the Once Clean Truck rule requires truck manufacturers to sell an increasing share of electric trucks each year, with the goal of making all new trucks sold in California zero emission by 2045. However, even though battery technology has become more advanced, the electric trucking is still heavily restricted by the operational range due to the much less energy density of lithium-ion batteries than fossil fuel. The electric trucks would require multiple recharging for long distance and transportation and cost delays. To reduce energy costs and relieve the range anxiety for electric trucks, connected vehicle technology emerges as one potential solution to improve energy efficiency via information sharing and vehicle-to-vehicle or vehicle-to-infrastructure coordination. Eco approach and departure at signalized intersection are particularly promising for energy saving through the vehicle-to-infrastructure communication. The intersection traffic signal would broadcast its current signal state and timing to the vehicle. Using the broadcasted signal phase and timing information and vehicle dynamics, the HOTS CV would calculate an energy efficient speed profile to follow until it passes the intersection. Electric trucks receive little attention in the EAD research. Therefore, the purpose of this research is to propose an EAD system for electric trucks that can reduce energy consumption and pollutant emission. There will also be discussions about the eco-driving impact on non-connected vehicles and multiple connected vehicles. When a connected eco truck approaches the signalized intersection, some types of information are fed into the algorithm to derive a safe and energy-efficient speed profile for the host vehicle. First is the longitudinal distance from the current location to the intersection. Then is the current time step, the instantaneous speed of the vehicle at the current time step, measured by onboard diagnostics or GPS devices. The fourth one is the lookout distance, which means within the lookout distance, cellular vehicle-to-everything technology enables direct real-time communication between the vehicle and traffic signal. The signal phase and timing messages are broadcasted to the connected vehicles. The vehicle-equipped radar could detect front vehicles for the emergency brake or queue prediction. The last one is the vehicle dynamics, which include the energy consumption model of the electric truck. The method we use for this system is what we call machine learning-based trajectory planning algorithm. The graph-based trajectory planning algorithm was developed using unique dynamic 3D vehicle states, the time, distance, speed, to represent the nodes in the graph, and energy consumption for state transition to represent the weight of the directed edge. Then the problem is converted into finding the shortest path from the source node to the destination node. To save the computational time, a random forest is then trained using the data created by the graph-based algorithm. The input of the random forest model is the 3D vehicle states, and the output is the optimal speed for the next time step. The EAD system is divided into two parts. The offline part trains a random forest model using the output of the graph-based model, and the online part runs in real time by the electric truck for eco-driving using the trained model. As shown in the figure, the 3D states collected by the host vehicle are fed into the graph model. Using the direct energy model of the electric truck, the optimal speed could be derived using the Diaz-Ross algorithm. The input-output pairs are collected and then used as input to train the random forest model, and the trained model is then used as part of the online model for real-time computation. In the online system, once the electric truck enters the communication zone of the connected signalized intersection, real-time vehicle states are collected and fed into the system. First, the connect vehicle equipped radar will detect whether the front or side vehicles are far enough so that it's safe to start eco-driving. Then it will calculate whether the distance and time in current phase are enough to pass the intersection. Finally, the vehicle states will be fed into the trained random forest model, and optimal speed at time t is calculated, and the system will loop into the next time step, t+1. We use Vissim to test the EAD system. A dynamic link library interface was developed to communicate between the simulation environment and the EAD model, so that the host vehicle could follow the output of the system for eco-driving. Vissim will broadcast the vehicle type, the speed, ID number, current time step, distance nearest front or side vehicles, and signal information. The vehicle type and ID number will help determine the vehicle dynamic model for energy calculation. The distance to the nearest front side of vehicles will not only ensure safe driving and avoid dangerous movement or lane changing, but also help estimate the queue length of the intersection to adjust the passing interval. The vehicle's speed, current time, and signal information will help calculate the optimal speed trajectory to pass the intersection. And after all the information was processed within the system, the optimal speed of the next time step will pass back to Vissim for the host vehicle to follow. Since the trucks have unique acceleration and deceleration patterns, we recalibrated the desired acceleration and deceleration model in Vissim based on real-world truck data, considering the vehicle dynamic capability and driving style. The acceleration and deceleration constraints also restricted the number of child nodes in the graph. We created a single intersection with 3 lanes and 1 vehicle input source. Inside Vissim, different vehicle composition, volume, and electric truck percentage could be adjusted to study the energy and pollutant impact of the proposed system to both the single vehicle and the entire system. The phase planning of the signal was adapted from the real-world pre-timed signal at Alameda Street in the city of Carson. For the results, first, the time, emission, and energy are almost linear to traffic volume. And the difference of the values between baseline and the EAD, the algorithm increases as the traffic volume increases. The system reaches the largest electric energy saving at 300 vehicles per hour and a 10% penetration rate, and the smallest electric energy saving at 1,200 vehicles per hour and a 100% penetration rate. In general, the entire system can reach the same time consumption as the baseline when the traffic is moderate, and slightly higher time consumption when the traffic is heavy. We also found that system emits more pollutants as the traffic volume and penetration rate increase, showing a negative effect in terms of pollutant of the EAD system, EAD to the system. This is mainly caused by the non-cooperative driving behavior of the algorithm. The unique driving profile derived from the EAD algorithm is affecting other non-connected vehicles and causing them some unnecessary acceleration and deceleration. In the end, as shown in the table, when all the trucks, which are about 20% of all vehicles, are replaced with the electric connected trucks, the hydrocarbon, carbon dioxide, and the PM 2.5 are roughly reduced by 50%. The time remains the same. The carbon monoxide and the NOx are reduced by around 3% and -3% respectively, meaning the main NOx resources are trucks and the carbon monoxide resources are cars. So as a conclusion, this research proposed an EAD system for electric trucks to approach a pre-time signalized intersection. The simulation results from Vissim show that the system could achieve up to 7.8% energy saving without the sacrifice of time, but could perform less effective when the traffic volume and penetration rate increase. In the future, we want to combine the cooperativity and the EAD to reduce the negative effect of the increasing penetration rate. We also want to extend the scope to corridors or networks and study the energy optimization approach for multiple intersections. That's all for my presentation. Any questions?
All right, thank you for presentation.